All right, so again, this is our last week of class. Uh, some respects, it seems like it's been forever since we started this. In other respects, it seems like it went by really quick. But we're down to class today through Thursday, and then our fourth and final test four, final exam, whatever you want to call it, next Tuesday morning at 8 o'clock. So uh, that's what's left. And we got a couple things to do this week. We started talking Friday that all of chapter 12 is has to do with the deflection of beams. That's what it's really the only thing in chapter 12, but there's a bunch of different methods and ways that we can do this. And I told you Friday we were going to look at two. And the first one of these that we're going to look at is what's called this double integration method. Right? And we got to this relationship on Friday. We saw that the second derivative of y with respect to x was equal to our moment function divided by EI. And so we're going to talk about this a little bit in general, and then we'll discuss how we're going to go about solving this. Y is the deflection of this beam. That's what we're after. We want to know what the function for y is. What we have here is we know what the second derivative of y is equal to. So we gotta solve this and get to what the actual function y is equal to. And what this is actually it's a differential equation. We're going to have to solve this differential equation. Now, here's where in normal class, I usually ask, by show of hands, how many have taken differential equations. And usually I find a good number of students in mechanics and materials have taken DE, but there's also quite a few who have not. So if you have not had DE yet, don't worry. Trust me, I'm going to show you how to solve this. It's real simple, easy differential equation to solve. Maybe you could argue probably about the simplest type of differential equation to solve. And for those of you who haven't had DE, this is kind of what you're going to do in that class is you're going to solve equations like this, where you're going to know, what the first, second, third, fourth, fifth, whatever derivative of some function is, and you're trying to get to the actual function itself. And it depends on what type of differential equation you have, determines what method you go about solving this. So before I go any further telling you how to solve this, I'm assuming there's at least a few of you here in attendance today who have had DE. And so this question would be directed toward you. Not asking how to solve it, I just wondering if you remember what type of differential equation that is. So anybody who's had DE, if you recognize what type of differential equation that is, you can just type it in the chat if you want to take a stab at it.
Is it separable?
It is separable. There's a little more descriptive. I got another what I was looking for is Arvin replied. It's a second order variable separable differential equation. That's what type of DE this is. It's a second order variable separable differential equation. Again, you don't have to know this to be able to solve this, but just FYI. Again, the second order comes from we got the second derivative of our function. Variable separable implies we can separate the variables. We've got all of our y's on one side and our x's on the other. And what makes this really easy to solve is if you can separate the variables like this, then all you have to do is integrate both sides. And how many times you have to integrate depends on what order it is. So we can solve this just by integrating both sides. In this case, we got to integrate both sides twice. So we integrate this left side once, we're going to get the first derivative. When we integrate the left side again, we actually get the function y. That's what we're after. Now, a couple of notes. One, we're assuming that e and I are constant. With respect to x. Remember, when we got a beam, x is our longitudinal direction. So what this assumption says is we're assuming the material does not change as we go down the beam. Beam's all made out of the same material. The second thing, we're assuming I is constant as you go down the length of the beam. That's saying that the cross-section does not change. It stays constant. Now, there are beams where the cross-section does change. We call those tapered beams. The cross-section either gets bigger or smaller as you go down the beam. That's a problem for a later class. Okay, we're not going to encounter anything with those circumstances in this class. We're assuming the cross-section is constant and the material is constant. Also, just notation-wise, I spelled that right. The textbook uses V instead of Y. And this is one of the few times where I can't stick with the notation the book uses. It's not that uncommon. I'd say if you picked up, a bunch of different mechanics and materials books, about half of them use V and half of them use Y. So this is, again, my personal preference. If I'm looking at a beam, I'm thinking X and Y here. Y is my displacement. I'm not sure the motivation for using V instead of Y, but I'm going to use Y. Obviously, if you look at our differential equation, I'm using Y instead of V. But I did want to point that out. So when you look at the examples in the book, you start seeing all these V's and didn't want you to get confused and figure out, well, what's the V? He's just using V instead of Y. And other kind of general note here, our moment function, it does vary with respect to x. And if you remember back at the beginning of chapter 6, everywhere the load changes, our shear force equation changes and our moment equation changes. So V will vary down the beam. That's why I'm showing it as a function of x. And it will be determined. So basically, we got two things. If we know this relationship, we're going to use the method we did back in the first section, chapter 6, to find our moment function. And then we got to solve the differential equation. So those are our two things we got to solve. So this will be determined by method of sections. It's identical to what we did back in section 6.1. The very first way we started talking about shear moment diagrams. And I told you then, you didn't have to do that to draw the shear moment diagrams, but you did need to know how to do that because later we were going to use it to find the moment equation, and that's where we're now at. So everywhere the load changes, you're going to have to cut the beam at some arbitrary location X, solve for that internal bending moment m. That's what goes in this differential equation. All right. So once we get that moment equation, then we go back to what I mentioned a minute ago. Right? We can solve this just by integrating twice. So if we've got our second derivative of y, and e and I are constant, I'm just going to pull those out. Right? Write it like that. We integrate both sides twice, and when we integrate the left side, this is now going to give me the slope is the first derivative of that function, and it's also equal to, if you want to use theta, recall here we're talking about very small angles, so for very small angle theta, the slope, which is just equal to tangent, right? That's opposite over adjacent, is essentially equal to the angle theta. All those we can kind of use interchangeably. And that's what dy dx is. It's the slope. And it would be equal to, again, we can just pull that 1 over ei, it's a constant, so pull it out. So we're going to integrate this moment function with respect to x. Now when we integrate with the indefinite integral, we have to add a constant of integration. So this will give me what the slope, or the angle that beam is directed. And then we just integrate again, and we actually get the deflection. Right? That's what y is. It's the deflection of that beam. And it would be 1 over ei. And so whatever we get after we integrate the moment there, we integrate that again. This would actually be the second integral of the moment. You integrate a constant, you just get the constant times x, and then we get a second constant of integration. Right? So this is the process we're going to go through. Once we find that moment equation, we integrate it once to get slope, we integrate it again, get the deflection. And that's what we're going to get here. We're going to get y as some function of x. And if you graph that function, it is the actual shape of that deformed beam. That's what this is. Now, we're not going to graph any of these equations, but if you did go through it and actually graph it, it would give you the shape of that deformed or curved beam. That's what we're actually getting here. Now, a little bit about the constants here, how we're going to go about finding those. But stop just a second. Any questions at this point? How we're going to go about finding our moment equation, and once we get the moment equation, how we integrate twice to get our deflection curve. All right, so let's talk a couple minutes about how we find these constants, and then we'll go through and work a problem. So again, C1 and C2 are just our arbitrary constants of integration. And these will be found by using one of a couple methods. Sometimes you may have to do both of these things. Sometimes the first one is sufficient. We can find some and sometimes all of these constants of integration just by using our boundary conditions. And now here's where the big difference between mechanics and materials class and DE class. DE class, you'd probably just be given what some boundary conditions are. here we got to use what we know about beams and how they're supported to determine what those boundary conditions are. And basically, we're going to see two things. We're going to have zero displacement at a support. So it doesn't matter if it's a pin support, roller support, fixed support. Right? It keeps it from moving up and down. We know the displacement, y, is going to be 0 at that, whatever x value is. And we also have zero slope at our any fixed support. Or maybe I'll also add in we'll stop there. We won't go any further there. If you have a fixed support, not only does it prevent it from moving, it prevents it from rotating. And so we know the slope, or the angle theta, that second equation up here, would be 0 at that x value. And I think if maybe I draw a picture, this will maybe it'll be a little clearer. If I got a beam like this where I've got a pin support and a roller support, and I don't want to say this beam's got some length L. So I know at this end, when x is 0, y is 0. Right? That beam does not move up or down at that pin support. So I know when x is 0, y is 0 at that support. Over here at the right end, I got this roller support. It keeps it from moving down anyway. So I know the beam doesn't move down there either. So I know when x is L, y is 0. So we can plug in those known values for y at these two known x values into our equation up here and solve for those constants. All right, that's how we're going to go about solving for these constants. Also, I mentioned a fixed support. Right? If you've got a fixed support, again, here, the beam, maybe it performs like this. Put some load on here. Right? It's going to bend down. Over here with the fixed support, again, it's some length L. Maybe we put a coordinate system on here. Again, they apply some force. This is going to cause the beam to bend down like that. But what I know here, when x is 0, it's fixed. It can't rotate. So right at that end, when x is 0, the angle theta is also 0 there. And that's not 0 out here at this end. It's bent. But right there at that fixed support, it can't rotate. So right at the end, the angle's 0. And we also know it can't move up or down there. So we know when x is 0, y is 0. So there's two boundary conditions. We can plug in those known values up here in our two equations and solve for those constants. Now, one other thing you can use sometimes, and you may or may not be able to use it to find your constants, but it's also a good thing to know here. One other thing, if you've got a situation like this, where you have your maximum displacement, I know the slope is 0 at that point also. So I know theta, which is, again, the slope or the first derivative dy dx, is equal to 0 at y max. So if you know where the maximum displacement is, you could use that to solve for one of your constants. You could use the fact that, again, theta is 0 at whatever x position y max occurred, and you could use that. Now be careful with that, because most of the time you're not going to be able to just look at it and know where the maximum displacement occurs. for a beam like this, if your loading is perfectly symmetric, like say we put this concentrated force right in the center halfway, then I know from symmetry the maximum displacement would be at x equals L over 2. But if that applied force is not right in the center, halfway down this beam, the maximum displacement does not occur where that load is applied. And it does not occur halfway down the beam. More often than not, you would use this to actually find where that maximum displacement occurs. Set dy dx equal to 0 and solve for x to find out where that happens. But I did want to mention that because occasionally, due to symmetry, you'll know that the maximum is going to be, say, right in the center halfway. And if that's the case, you could use it to find your boundary condition. Again, I'll repeat. Otherwise, normally where you would use this is to actually find where your maximum displacement is and what it is. Right? But now sometimes this is not going to be enough. We're not going to always be able to determine all of our constants just from boundary conditions. So occasionally we also have to employ what the book refers to as continuity conditions. Basically what this is it's saying this is one continuous beam, and remember, if the load changes, we have to cut it again and we get separate equations. But where those two equations meet have to give you the same values, right? Because it's a continuous beam. It's one nice smooth curve. So this is the displacement and slope must be equal where these different sections meet. Again, I think I'll draw a picture here might help this a little bit. Let's say we got a situation like this where we've got a pin and a roller, and then we've got some force acting here at distance A. Again, this is going to cause this beam to bend, right? And this is going to be exaggerated. If we have a beam that bends like this, that much, relative to what the beam looks like, we're in trouble. You wouldn't want to drive across a bridge that did that. So again, these displacements I'm drawing are greatly exaggerated. Remember, we're always assuming we're going to have really, really small angles here, but for illustration purposes. So if you had a beam like this, and we'll actually look at an example similar to this tomorrow, you'd have to cut it twice, right? You'd have to cut it one time between the end and where that load is applied, right? And you would get one moment equation, right, for this part of the beam. You'd have to come over and cut it past that loading change. And for this part of the beam, you'd get a different moment equation. Right? So consequently, that's going to give you different equations for slope. It's going to give you a different equation for the displacement. Right? So for this part of the curve, we're going to get, say, theta 1 x and y1 of x. It's going to give me the slope and displacement for this part. And again, that comes from that moment. Over here, right, we're going to get a different set of equations. I'll get a different equation for slope, a different equation for displacement. But right here, where they meet, at x equals a, they got to give me the same value. And so that's what this says, is that theta 1 at x equals a has got to equal theta 2 at x equals a. And the displacement. Right, if I plug x equals a into this equation, right, I got to get the same displacement as I do if I plug x equals a into this equation. Where they meet got to give me the same values. All right, any question about, again, discussion on how we're going to determine those constants of integration? All right, so I think that's enough like general stuff. Let's see if we can go through and solve one of these. There's several good examples in the book. I encourage you, as always, look at those. In addition to the one that we're going to work today and tomorrow. All right, I can speak up if you need another second, or can I change page? All right. Now, for those of you who have had differential equations, one thing you may know that sometimes, sometimes solving some of these differential equations can get a little lengthy, and that's going to be the case here. Some of these beams not going to be too bad. We're going to do one today where it's not so bad. We only have to cut it once. We're going to only get one equation, and it's not going to be such a long problem. But I'll warn you, some of these problems are, I'm not saying they're going to be hard, but they can be long. Because again, those of you who've had DE know solving some differential equations, it's not the shortest problem in the world. But this one's not going to be so bad. We're going to see if we can determine and I'm going to use the wording that the book likes to use here, the equation of the elastic curve. And this will be part A here, and will be part B. The slope and displacement at end B. All right, so let me draw my beam, and then I'll come back and talk a little bit more about the wording used there. We've got a beam's got a fixed support at the left end. This is A, and it's got a linear distributed load. It starts at the left end of 0 and goes up to a magnitude W naught at the end B here. And this beam's got some length L. All right, so back to the wording here. The equation of the elastic curve. That's just y of x. But this is the terminology he uses to denote that. And again, the elastic curve part is in there because, remember we talked about different materials, stress strain diagrams. You have the elastic region, right? That's where the stress is less than the proportional limit. We're not permanently deforming. That's where the terminology elastic curve comes in, is that we're assuming these beams are not being stressed so that they're experiencing permanent deformation. That's where we can use the small deformation approximation that we discussed earlier. All right, so that's what part A is. It wants to know what the equation for the displacement, this equation we get for y, if you graph it, is going to be the shape of this deformed beam. That's what we're after in part A. Part B out here, again, it's just asking for, what's theta B and what's YB. again, what's the slope or the angle and the displacement out here at this end B, right? Because again, this thing's going to bend down, right? We're going to have a curved beam, right? Once again, this is greatly exaggerated. In the real world, some of these beams you could hardly even see them move. The displacement's so small. All right, so this is my beam. We have support reactions here, this fixed support. And again, it's capable of providing these three reactions. Reaction force in the x and y direction, but AX is 0. We don't have any other forces in the x direction. But we do have AY and reaction moment there. So we need to solve for those. So that's what we're going to do first, is solve for my support reactions here. So that's the first thing up. Now, for this distributed load, we're going to replace this with this equivalent resultant force. And the equivalent resultant force for a distributed load is the area under the curve. This is a triangle. So it's just, again, going to be 1/2 base times height. Maybe I'll draw a new free body diagram over here. We got AY, we got MA, and we got this equivalent resultant force. Again, the area of the triangle is 1/2 base times height. So 1/2, the base is L, and the height is W0. Now that equivalent force has to act at the centroid. Now the centroid of a triangle is 2/3 from the little end or 1/3 from the big end, whichever way you want to measure it. But in this case, if we go from the little end, right, this thing is some length L. So this would be at a distance 2/3 of L from the end. This is B. So that's all I've done is replace that distributed load with its equivalent resultant force placed at the centroid of that distributed load. And now we can sum the forces in the y direction. I know it's got to be 0. I got AY going up. I got minus 1/2 W0L going down. And that's it. All right, just two forces. So AY, I'll just write as W0L over 2. And now we sum the moments about any point we want to and solve for MA. I would choose either A or the point where this equivalent force is. I'm just going to go with A. I'm going to eliminate as much as we can. So I've got my reaction moment MA. AY goes through point A, does not cause a moment. And then this is causing a clockwise moment. So minus W0L over 2. Right, that's my resultant force there, times 2/3 L. Now it's got to equal 0. So move this to the other side. It becomes positive. 2's cancel. Looks like W0L squared over 3, if I did my algebra right. So I found AY. It's W0L over 2, and it's acting up. My reaction moment, W0L squared over 3, it's the counterclockwise. All right, so now we're ready to, again, come out here some arbitrary distance x and cut this beam and solve for that internal moment equation. And so I'm going to draw a new picture. That was starting to get a little cluttered. And keep in mind, our result here, it's going to be good for the entire length of the beam. Right. because this distributed load goes the entire length of the beam. We don't have to cut this one more than once. We just pick any arbitrary location, X, cut it, and the equation we get will be good for the whole beam. We'll look at one tomorrow where that's not the case. We'll have to cut it more than once, and you just double the length of your problem when you do that. But again, that's something to look forward to tomorrow. So let's, again, come out here, this arbitrary distance X. That's where we cut it. Here at A, we found AY was W naught L over 2. We found MA was W naught L squared over 3. Yeah, that's just my support reactions that we found up there. Now I've got this distributed load. It's linear. Now obviously, if we go some arbitrary distance X, we're not going all the way to the end of the beam. This distributed load doesn't get all the way up to this magnitude W naught. And so we're going to have to determine what the magnitude of that distributed load is. Now here where we cut it, we've got a shear force, V of X, and we got a bending moment, M of X. Again, those internal shear force and bending moment are functions of X. And this is exactly what we did back in chapter 6, beginning of chapter 6. And so this is what we're after. It's that bending moment. So I've got to do something with this distributed load, just like I did up here, right? We replaced it with an equivalent resultant force. We've got to do the same thing. Well, in order to do that, we need to know what the magnitude of that distributed load is, again, in terms of what the maximum is. And I'm pretty sure I remember doing one similar to this back in chapter 6, and I mentioned that there's several ways you can do this. I kind of like using similar triangles. And so if we look at the big triangle, the length of the whole beam is L, and if that's the case, again, this side would be W naught. What I want to know is if I come out here some distance X, what's the height at that location? And again, this is just similar triangles. Wx is to X, as W naught is to L, and solve for Wx. And that's W naught X over L. All right, any question how we got what the magnitude of the distributed load is at this arbitrary distance X? And you can always check yourself, right? If you look at this, well, we know what it is at the end when X is L, so if you plug L in here for X, that's what you get. Well, if you plug L in here for X, the L's cancel and you get W naught. So I know this is right. But we got to replace that, again, with an equivalent resultant force, just like we did up there above. It's the area of the triangle. So it's 1/2. The base is X, and the height is W naught X over L. Oh, again, it's just the area of a triangle, 1/2 base times height. Just like up here, we place it at the centroid of the triangle, which I know is 2/3 from the little end, 1/3 from the big end. And up here, we sum the moments about the left end, so I denoted the location from, in this case, the little end. But here, it's to your advantage to sum the moments about the point where you cut it. And again, the motivation for that is if you sum the moments about this point, then we don't have to solve for the shear force. If you sum the moments about point A, for example, well, now we got to go calculate what V is, because the shear force V doesn't go through point A. So good suggestion here is to sum the moments about the point where you cut it. Again, this is so we don't have to find what the shear force is. So I'm going to sum the moments about this point. So I want to know what the distance is from this end to where that resultant force acts. In this case, it would be 1/3 from the big end. So if this is x, this would be x over 3 from where we cut it. So let's sum the moments about that point. Maybe we'll call it P. So if we sum the moments about P, set that equal to 0. I got the moment equation. One other thing, I don't think I mentioned this, but important here. Always assume M is in the positive direction. All right, remember we said a positive moment is a moment in this direction, right? Positive moment makes it concave up. And the reason for that is that if you go back to Friday, when we were deriving that differential equation, we actually had an absolute value in there that we got rid of by assuming that we had a positive moment. And so that's why we got to assume it's positive, so that the sign convention is compatible with our differential equation. That differential equation is assuming a positive moment. So that's why I assumed this moment going that direction. If you assume it in the other direction, your answer is going to be a negative of what it should be. All right, so we got our moment, m of x. We got this resultant force due to our distributed load is causing a positive moment. And I'm going to combine some stuff here. That would be what, W naught. I got an x times x is x squared. And then I got a 2 in the denominator and an L in the denominator. All right, that's my resultant force. If I didn't do that algebra right there, somebody speak up. And we multiply it times x over 3. That's the distance from point P. We got the moment that our support reaction AY causes. It's a clockwise moment. W naught L over 2. And that's times x. And then we got the reaction moment MA is in the positive direction. W naught L squared over 3. All that's got to add to 0. And we solve for our moment equation. So move everything to the other side. The signs are going to change. This is going to be minus W naught. I'm going to have an x cubed now. 3 times 2 is 6L. Move this to the other side, it becomes positive. W naught L x over 2. And then this one becomes negative. W naught L squared over 3. All right, so far, basically all we've done is a bunch of stacks to come up with that moment function. All right, that is the moment as a function of x. And remember, this is good for the whole beam. So that is my moment as a function of x. That's what we're after. That's what we need in order to solve this differential equation. All right, so now we're ready to take that, put it in our differential equation, and see if we can solve and integrate this thing. So I know the second derivative of y with respect to x, again, is 1 over EI. times that moment function that we just found. So it's 1 over EI W naught x cubed over 6L plus W naught LX over 2 W naught L squared over 3. Integrate both sides. So we integrate the left side, get dy dx. Or if you prefer to use theta, that's fine. It's the same thing. The 1 over EI is constant. But don't forget that. I see students all the time that forget and leave that off. So we just integrate this. It's a nice polynomial function. Integrating with respect to x, we get minus W naught. X cubed becomes x to the 4th over 4. 4 times 6 is 24. W naught L, here we get x squared over 2, and 2 times 2 is 4. And then minus W naught L squared over 3 times x plus C1. And then we got to integrate one more time. Now we'll actually get the function y, 1 over EI, minus W naught x to the 5th over 5 times 24 is 120. W naught L, here we get x cubed over 3. 3 times 4 is 12. W naught L squared, here we get x squared over 2 times 3 is 6, plus C1x plus C2. Right? Don't forget your constants. All right, we'll call this 1, 2, and 3. Just for identification purposes, because I may run out of the room here at the bottom and have to go over to a new sheet. All right, but any question at this point, how we took this moment equation, and we integrated once to get the equation for the slope, and we integrate again, and we get the equation for the actual displacement or deflection of this beam. All right, so now all we got left to do is we got to see if we can apply our boundary conditions to determine what those constants are. All right, so slide this up a little bit. So my boundary conditions. Here I've got a, remember, pull it back down. We got a fixed support here at A. All right, this is fixed. So again, this beam is going to deflect like this. But at this end here, again, when x is 0, the slope is 0. So when x is 0, the slope is 0. When x is 0, y is 0. It does not move up or down there. Right, those are the two boundary conditions I have for this beam based on how it's supported. So I can take this boundary condition that I know about the slope, and I can plug into equation 2, and we can solve for C1. Right, so we're taking this boundary condition. When x is 0, theta is 0. And equation 2, this equation here, we're going to plug 0 in here for theta, 1 over EI. And I'm plugging 0 in here for x. This is going to be minus 0, plus 0, minus 0. Everywhere there's an x, I plug in 0. All that's left is C1. All right, we can cancel the EIs, right? Because I got 0 is equal to this thing. So if I multiply both sides by EI, EIs cancel, and EI times 0 is still 0. So what I'll have left then is just C1 is 0. So I now know that is 0. Now I can take this boundary condition that I know when x is 0, y is 0. And I can plug in the, what I called equation 3 here, and we can find what C2 is. So I'm taking this boundary condition, And equation 3, my displacement, I'm going to plug 0 in here for y. And I know it's 1 over EI. And I'm plugging 0 in for x. So that's going to be 0. Plug 0 in. All these are going to be 0. Just like before, the EI's cancel. And I know C2 is 0. So this one worked out kind of nice in that we didn't have to do a whole lot to determine our constants of integration. They were actually pretty easy to find. And so now I'm just going to rewrite this on the top of the next page. And that's basically our answer, right? We just found what our constants are. So the answer to part A, my displacement, I'm looking at this. Let's see. I don't have room. Bear with me. I'll write it here. Is 1 over EI minus W naught x to the 5th over 120 L plus W naught LX cubed over 12 plus W naught L squared x squared over 6. And then C1 was 0 and C2 was 0, so that's it. So if I look at what I had, make sure I rewrote that correctly. Double checking. Looks like I've got it. Oh, no. This is supposed to be minus. So now that looks like what I got. So that's the answer to part A. So if you plug in any x value, you can determine what the displacement is at that. No? Somebody asked the first term should be to the 4th. Now I've got to the 5th. The moment equation. Okay. So that's my equation. One thing, note, there are no, I don't have any AY, MA is not in the answer. The answer is just in terms of those, what we were given, W naught, L, if you had a force P, there's no support reactions left in this answer. So if you solve this, and I bring that up because I've seen students do this before, they'll start with this and they'll just leave this as AY instead of actually solving for AY in terms of the load. And their answer has AY in it. Well, then you don't have an answer yet because if you don't tell me what AY is, you're missing part of the answer. Okay, is that clear? So your final answer should not have any support reaction like that. It shouldn't have any AY, BY, MA, any support reactions. You've got to solve for those in terms of the given load. Most of the problems you'll find in the book are like this. They don't have real numbers in them. It's P's and W naughts and L's. I know some people don't like those types of problems as well, but that's the way most of these problems are. So I know I'm like a couple minutes over, but give me just 1 minute because that's all it's going to take to answer part B is we're just going to plug x equals L. So if you go back to equation 2 on that previous sheet, theta B is the slope at x equals L. You just plug L in there for x, and so you get 1 over EI minus W naught L cubed over 24 plus W naught L cubed over 4 minus W naught L cubed over 3. So all I've done is go back to this equation, and where there's an x, I'm plugging in L. That's it. It's just plugging in x equals L. Those are all similar terms. You can get a common denominator. Again, due to time, we'll skip going through the math. I got W naught L cubed over 8 EI. Again, it's just terms in L, W naught, E's, and I's. There's no unknown support reactions in there. And then equation 3 we just found, YB, we're going to plug Y equals, X equals L in here for Y. And we get 1 over EI, W naught L to the 5th over 120 L. So one of those cancels, and it'll be L to the 4th. W naught L times L cubed is L to the 4th over 12. W naught L squared times L squared is L to the 4th over 6. Again, those are all similar terms. You can get a common denominator. I got minus 11 W naught L to the 4th over 120 EI. Notice both those answers negative. That's just indicating direction. That tells me that the slope is this way. The arrow. So if you look at the end of this beam, we have this beam, positive X to the right, positive Y was up, right? This beam is bending down. So that angle is negative. The deflection is down. It's negative. Positive Y is up. This beam moves down. Right? So not difficult, I don't think it should be. Again, not the shortest problems in the world. And this one we only had to cut once. So you can, again, imagine if you have to cut it 2 or 3 times, the problems just get longer. But longer doesn't necessarily mean difficult. Process is going to be the same. Any question about this one? All right, so again, sorry I went a couple minutes over, but I want to go ahead and get the final answer for this thing. And we'll do another one tomorrow. And then Wednesday we'll talk about superposition. Think you'll like that method better. It's shorter, much shorter. All right, any questions before I stop recording? All right, well, if you've got a question about something you want to stick around, you can do so.